Good day, dear students. Welcome to our regular lecture on logistics. Today we are looking at transport management systems, known as TMS. If previous topics were dedicated to warehouse processes within four walls, today we are stepping outside. TMS takes over the management of cargo from the moment it is loaded into the vehicle until it is handed over to the end customer. Modern transport logistics is the management of chaos. We deal with an enormous number of variables, hundreds of orders, different cargo dimensions, extremely tight delivery time windows, and tangled carrier tariffs. It can be confidently stated, a dispatcher's attempt to calculate an optimal delivery plan using ordinary Excel spreadsheets inevitably leads to so-called carrying error and colossal overpayments. That is why the focus of our attention today is a fundamental shift from dispatcher intuition to the mathematical precision of algorithms. A human is physically incapable of optimally considering hundreds of constraints every second, while specialized software does it in fractions of a second. Our main task in the modern supply chain is to achieve ideal indicators, where the status of each route is optimized, and the calculated time of arrival is always met precisely according to schedule. Let's look in more detail at how this is implemented in practice using modern software modules. Recall our previous topics where we analyzed warehouse management systems. They create an ideal structure and order, but operate exclusively within four walls. However, as soon as the truck doors close and it leaves the distribution center gates, the cargo enters a world of dynamism and unpredictability. TMS takes over the relay race at this very moment, managing all processes from the physical loading of the vehicle to the final handover of goods into the client's hands. The main management challenge of transport logistics lies in the staggering number of variables. Imagine the operational day of a large distribution company. Hundreds of disparate orders, different dimensions and physical properties of goods, strict customer requirements regarding receipt time, so-called time windows. Add to this completely different pricing principles from logistics partners, a real menagerie of tariffs. For quite a long time, dispatchers tried to tame this mass of information using ordinary spreadsheets. However, the human brain is not capable of simultaneously calculating thousands of spatial and financial combinations. The result of this approach is what is called carrying error in professional circles. These are extremely inefficient situations where half-empty trucks chaotically roam the city, or when a company orders transport that does not match the actual volume of cargo. Therefore, scaling a business is impossible without a tool that replaces manual errors with mathematical calculations. Imagine a classic logistics paradox. Why can a kilogram of ordinary medical cotton cost as much to deliver as a whole box of iron? It would seem that the physical weight of both cargoes is absolutely identical, totaling 1 kilogram. However, iron nails can easily fit into a very compact box, while cotton, or for example foam plastic, will occupy a significant portion of the truck's cargo space. The fact is that there is no single standard for pricing in the logistics services market. Transport Company A may tariff a trip strictly by mileage. Company B sets a fixed price per trip, a so-called freight charge. But courier services, which we all regularly encounter, use a much more complex matrix that necessarily takes into account the delivery zone and volumetric weight. Since space in a truck is limited, it is important for carriers to evaluate the space the cargo occupies in the cargo compartment, not just its actual mass. In international practice, the IATA standard is most often applied for this. The calculation is carried out using the following formula. Volumetric weight equals volume, i.e., length multiplied by width and height in centimeters, divided by 4,000. It is worth noting that depending on the commercial policy of a specific operator, a divisor of 5,000 or even 6,000 may be used instead of 4,000. So, if we take a box measuring 50 by 50 by 50 centimeters with our ultralight goods, after a simple mathematical calculation, we will get a chargeable weight of 31.25 kilograms. This means that for the delivery of a 1 kilogram package, you will have to pay as if it weighs over 30 kilograms. This is where the TMS tariff management module comes into play. It automatically digitizes this diverse menagerie of tariffs into a single transparent database. As soon as a new order enters the system, it instantly runs the cargo parameters through all available tariff grids. The dispatcher no longer needs to spend time on calculators or calls to partners. The system automatically calculates and displays the most profitable exact delivery costs for each available counterparty. This is the first step towards the complete elimination of the subjective factor in managing transport costs. Once the delivery cost is calculated, the next logical question arises: to whom exactly should we entrust our cargo? Imagine you are managing the logistics of a large brand. It would seem that the simplest business rule is to always choose the contractor with the lowest price. However, in real professional logistics, such an approach is extremely dangerous and often results in huge losses. A modern transport management system works with a single database of carriers, but makes its selection based on the SLA principle, i.e., the service level agreement. In this paradigm, the reliability of fulfilling obligations is placed significantly higher than the basic price. How does this work algorithmically? The module continuously performs SLA analysis based on historical data. The system remembers how often a specific carrier was late for loading and whether cases of goods damage were recorded during its trips. For example, if we are sending a batch of ordinary bottled water, we might allow ourselves to take a risk and hire the cheapest carrier. But what if we are loading a batch of flagship smartphones or extremely important medicines? For such specific and expensive goods, the system automatically rejects a cheap but unreliable carrier with a low quality rating. The algorithm will independently suggest a more expensive, but more reliable partner to guarantee the safety of the goods. In addition, for large enterprises, this module implements an automatic tendering tool, which in international terminology is called freight tendering. Instead of the dispatcher spending hours calling car fleets, the system creates a virtual auction of bids. For example, a request for an urgent Kiev-Lviv trip is formed. This request is instantly sent to a pool of pre-approved transport companies. Contractors submit their proposals, and the system itself collects bids, compares them with reliability history, and automatically determines the winner, assigning the trip to them. This approach completely eliminates the subjective human factor and provides an absolutely transparent mechanism for selecting the best performer. One of the most powerful tools for radically reducing logistics costs is freight consolidation, which we often call the mathematics of savings. The fundamental idea of this process is to transform small partial loads, in international terminology this is the LTL format or less than truckload, which is very expensive, into full and economically viable FTL trips, i.e. full truckload. Let's consider a typical business case from real practice. Suppose our distribution company received 5 separate orders, each weighing 2 tons, which need to be delivered to different B2B clients in Dnipro. If we try to send them separately, using door-to-door courier services, the logistics component will consume all the profit from the sale of the goods. How does the algorithm work in this situation? The system analyzes the incoming flow of applications, instantly detects a match by geographical vector and time requirements, and suggests to the dispatcher that these 5 orders be consolidated into one. We hire one large 10-ton truck, which for a fixed tariff brings the entire combined cargo to Dnipro. Then the cross-docking mechanism is launched. The goods, without long-term storage, are reloaded onto local small-tonnage vehicles, which then deliver them directly to the final points. The main value of this module lies in changing the very paradigm of decision-making. We forever get rid of dependence on the dispatcher's personal intuition or their harmful habit of assigning trips to a favorite, familiar driver. Every decision of the system becomes exclusively mathematically justified, and as a result, the most economically advantageous for the company. When a company has its own vehicle fleet or leases dozens of cars for daily order delivery, a fundamental need for routing arises. Historically, this looked like the dispatcher sitting in front of a map and relying solely on their own experience, simply grouping invoices by city districts. But today, such an approach is absolutely unprofitable. All modern route optimization is based on the classic mathematical model, called the Traveling Salesman Problem. Its essence lies in finding the shortest path that passes through a given number of points only once within mandatory return to the base or warehouse. The problem we face in practice is the factorial growth in the number of options. Let's look at specific figures. If our driver needs to visit only 5 unloading points, there are 120 possible route combinations. With such a volume, an experienced logistics specialist can still cope mentally. But if there are 10 points, the number of options instantly increases to 3.6 million. And now imagine a standard shift for a city delivery courier. It's about 20 orders. The number of possible combinations here is already calculated in quintillions. No human is physically capable of calculating such a massive amount of data, so the dispatcher always chooses the first logical option, in their opinion. Imagine a scatter of addresses on a map. Most of us would intuitively connect them into a visually smooth circle, moving from the closest point to the next. But mathematical modeling proves that this is a trap. A computer algorithm builds the path so that it is cumulatively the shortest for the entire trip. Even if the lines on the map intersect and look like an absolutely illogical spiderweb, such an optimally calculated path turns out to be, on average, 20% shorter than an intuitive human route. On the scale of a single trip, this difference might seem insignificant. But let's take, for example, a company with a fleet of 50 cars that deliver hundreds of orders every day. These 20% of extra mileage daily amount to millions of hryvnias in colossal losses on fuel and depreciation by the end of the year. That is why the competition between human and algorithm in modern transport logistics has long and undeniably been won by mathematics. Continuing the topic of route building, it is important to realize one fundamental truth. The shortest path on a map is by no means always the cheapest or fastest path in real life. The fact is that modern multi-factor optimization algorithms build a route while simultaneously satisfying dozens of strict constraints. First and foremost, these are time windows. Imagine that our client A, for example a large supermarket, accepts goods strictly from 7 to 9 a.m., and another client, a city cafe, expects delivery only from 10 a.m. to 12 p.m. The software system builds the route precisely so that our driver does not arrive at closed doors and does not wait for several hours idle. The second critical factor is carrying capacity and dimensions. The algorithm continuously monitors that the total weight and volume of goods do not exceed the technical characteristics of a particular vehicle. For example, a limit of 1.5 tons or a certain cargo compartment volume. The third level of complexity is added by road restrictions and city traffic jams. TMS is deeply integrated with mapping services and takes into account real-time traffic, prohibitions on truck entry into the city center, the presence of one-way streets, and even dimensional restrictions of bridges. Finally, there's another interesting professional case: minimizing left turns. Many global logistics companies, including UPS, deliberately incorporate a prohibition or maximum reduction of left turns into their routing algorithms. Why? Because in countries with right-hand traffic, a left turn always requires a long wait at the intersection. And this means that the vehicle burns excess fuel and, most importantly, the risk of getting into an accident statistically increases significantly. The most complex and expensive stage in the entire routing system is the so-called last mile. This is the final stage of delivering goods directly to the door of the end consumer, which is very important for the e-commerce sector, B2C segment, and courier services in general. In professional practice, we encounter an incredible paradox of cost distribution, which forms the total delivery cost. Let's look at the structure of a typical route. Trunk transportation, say, from a distribution center in the suburbs to the city limits, accounts for approximately 95% of the total physical distance. However, the last mile itself, which constitutes a minimal 5% of the journey, accounts for up to 50% of all logistical costs of the enterprise. Why is this short final segment so expensive for businesses? First of all, due to the extremely high density of small stops. In the urban cycle, a courier stops every 5 to 10 minutes. The second factor is the absolute unpredictability of the client and urban infrastructure. Often, a perfectly planned schedule breaks down against harsh reality. The client simply doesn't answer the phone, the elevator in a multi-story building unexpectedly breaks down, or the driver spends 20 minutes looking for a parking spot in a crowded residential complex. Furthermore, the last mile is constantly subject to dynamic changes. The system must recalculate the path literally on the fly, as new express orders may arrive while the vehicle is already en route. This is where algorithmic support becomes a lifesaver. The implementation of specialized TMS modules for last-mile management allows for a 15 to 25% reduction in total mileage at this complex stage. Imagine these figures on an annual scale. This is gigantic savings on fuel, a significant reduction in vehicle depreciation, and rational use of courier drivers' working time. Continuing our conversation about the unpredictability of urban logistics, it is worth noting the evolution of the planning approach itself. Classical routing always relied on a rigid travel plan, formed at the beginning of the working shift. The driver received the approved route and set off on the trip. But real life makes its adjustments. What to do if a serious accident suddenly occurs on the usual path or a deadlocked traffic jam forms? The modern pace of business demands instant adaptability from us. To solve this problem, algorithmic dynamic routing based on artificial intelligence is used. The software continuously recalculates and optimizes the courier's path directly during the trip, in real time. This need is particularly acute today, with the rapid development of the Q-commerce segment, i.e., quick commerce, and express delivery services for food or medicines. For example, a courier is already moving according to the plan, and suddenly a new super urgent order drops into the system in a neighboring block. A few years ago, the dispatcher would have had to call the driver, try to fit this point into the schedule, risking being late for other clients. Today, the system does it differently. It instantly discards the old plan and lays out an entirely new route. The algorithm automatically rebuilds the sequence of unloading points directly on the driver's tablet or smartphone. And most importantly, this recalculation occurs taking into account all existing obligations to guarantee that the promised time windows for previous clients are maintained. Artificial intelligence takes over the processing of colossal amounts of data about the current road situation, completely freeing humans from the stress of making urgent decisions under time constraints. The challenges of the last mile are closely related to a classic problem such as sharp spikes in demand. Imagine a typical situation in large retail. The period of global sales, known as Black Friday, or the pre-New Year holiday season arrives. The volume of orders instantly skyrockets several times over. The traditional extensive approach would require the enterprise to maintain an inflated private car fleet and a huge staff of couriers. However, from the standpoint of financial efficiency and asset management, this is a disaster because during ordinary off-season months, these vehicles would simply stand idle, generating pure losses for the company. A modern engineering and management solution is the crowdsourced delivery model, often called Uber for logistics, in professional circles. How is this technically implemented? Modern TMS systems set up deep integration via API protocols with gig economy platforms, such as Glovo, Uber, or Uklon. When the system analyzes the flow of applications and determines that the regular drivers are already 100% loaded and physically cannot deliver the remainder, it automatically initiates the creation of requests on these partner crowdsourcing platforms. In logistics, we call this process cutting demand peaks. Thanks to such an architecture, the enterprise gains the ability to flexibly and instantly satisfy peak customer needs. The business effectively leases third-party couriers for precisely the time and volume of work that is directly necessary at a given moment. This allows the company to maintain a high level of service without the need to freeze capital in purchasing additional transport. After the algorithms have ideally planned all routes, the stage of their direct physical execution on the road begins. Planning is mathematical theory, but operational reality is always associated with unpredictability. Traffic jams, breakdowns, or queues at borders. To effectively manage this chaos, we need telematics, a hardware complex that combines telecommunications and informatics. In the traditional outdated logistics model, a dispatcher spends the lion's share of their working time on endless phone calls to drivers with a single question: where are you now and when will you be at the point? This is exhausting and inefficient micromanagement. Modern TMS fundamentally changes this approach by introducing the paradigm of management by exception. What does this look like in practice at an operations center? Dozens of vehicles are displayed on a specialist's monitor, but the dispatcher focuses attention only on those highlighted by the system as problematic. As long as the truck or courier vehicle moves according to the approved plan, the system does not highlight them, and the dispatcher simply does not intervene. But if continuous GPS tracking detects a deviation, for example, calculates an inevitable delay of more than 30 minutes, records a departure from the permitted route, or prolonged downtime, a red alarm notification instantly appears on the screen. In practice, the highest value of this module is its work with the ETA, the estimated time of arrival. Geolocation data is used not just to display a green on the map, but for its constant recalculation in real time. If a vehicle is stuck on the highway due to a serious accident, the ETA inevitably shifts. The main advantage is that the algorithm is proactive. It automatically generates and sends an alert to the client about the delay, even before the promised time window expires. This fundamentally changes the level of service, transforming logistics from reactive to predictable. One of the most painful points for any vehicle fleet is fuel costs, which typically account for 30% to 50% of all operating expenses of an enterprise. Information systems allow us to effectively combat two main problems in this area: non-targeted use and inefficient driving style. Technically, this control is implemented through deep integration. Telematics equipment connects to the CAN bus, the internal information network of the vehicle, or uses special cut-in fuel level sensors in the tank. Let's look at the mechanism for controlling fuel drains. TMS not only records the fuel level, but continuously compares its actual consumption with the normative indicator for a specific route. If the algorithm notices a sharp drop in the tank level that absolutely does not coincide with the mileage driven, or records a refueling of a smaller volume than was just paid for with a corporate fuel card, it instantly generates an alarm notification for the company's security service. This allows for stopping theft in real time, rather than dealing with shortages at the end of the month. The second, no less important aspect is the implementation of the eco-driving concept. Even the most honest driver can cause losses to the business due to aggressive or negligent driving style. The system meticulously collects data on driving style. It accurately records every harsh braking, systematic engine over-revving, and prolonged idling. There is a very typical example. A driver arrived at the warehouse, and while waiting for their turn to unload in winter, simply lies down to sleep with the engine running to heat the cabin. Although the car is stationary, the company continues to burn money. Based on these objective metrics, the system automatically forms a driver rating, which in international companies we rigidly tie to the bonus system. Thus, the algorithm itself cultivates a culture of economical driving within the team. Modern telematics has long gone beyond simply determining coordinates on a map or basic fuel-level control. The new absolute standard of safety, especially in international transport companies, is the deep implementation of AI-based video analytics, known as AI dashcams. Technically, this is implemented as follows. Special AI video recorders are installed in the cab of a long-haul truck or courier vehicle. Their fundamental difference from ordinary car cameras is that computer vision algorithms are capable of independently recognizing objects and analyzing behavior in real time, absolutely without human operator intervention. The main function of this technology is the preventive prevention of road traffic accidents. The algorithm continuously monitors the driver's physical condition. For example, the system is able to instantly recognize so-called microsleep, an extremely dangerous state of fatigue when a person blacks out for literally fractions of a second. The camera clearly records closed eyes, frequent yawning, as well as any distraction, such as using a mobile phone while driving or smoking during movement. In parallel, external lenses monitor dangerous maneuvers on the road itself, critical failure to maintain a safe distance or sudden lane departure into oncoming traffic. As soon as artificial intelligence detects the slightest threat, the device instantly generates a danger warning and emits a sharp audible signal directly in the cab. This allows the driver to instantly awaken, react, and prevent a catastrophe. Simultaneously, a short video recording of the incident is automatically sent to cloud storage. Subsequently, the fleet's security service analyzes these video fragments to conduct targeted preventive work with personnel. This investment pays off extremely quickly, as it saves not only expensive cargo and equipment, but also human lives. One of the most interesting and powerful automation tools in modern transport management systems is geofencing technology, or the creation of geozones. What is a geofence from a technical point of view? It is a virtual perimeter that we artificially outline on a digital map. For example, we can set a radius of exactly 500 meters around our client's distribution center, or define the territory of a customs terminal, or even a restricted access zone. The main operational magic begins the moment the vehicle's GPS tracker crosses the boundary of this invisible zone. The system doesn't just record the fact of crossing, it automatically initiates a whole cascade of pre-programmed actions. Firstly, an immediate automatic status change occurs. As soon as the truck enters the geofence of the unloading warehouse, its status in the system automatically changes to arrived. The driver no longer needs to spend time calling the dispatcher or checking in at the gate. Secondly, this dramatically accelerates warehouse processes. A colossal problem has always been queues of trucks at ramps, but now, say, 10 kilometers before the vehicle's arrival, when it crosses the outer geofence, the system independently sends a message to the warehouse worker's terminal. Prepare dock number 4, the truck will be here in 15 minutes. This completely eliminates vehicle downtime waiting for an available spot. The third, supremely important aspect is cargo security. If a vehicle carrying expensive electronics suddenly deviates from a strictly approved route corridor or leaves a secure parking zone during overnight parking, the system can automatically block the engine and call a rapid response team. And finally, the most revolutionary global logistics trend, which we are actively embracing, is the combination of geofences with blockchain technologies and electronic document management. Classic paper waybills are being replaced by electronic ones, known as e-CMRs. When a truck crosses the geofence of an unloading point, and the warehouse worker confirms receipt with a digital signature on their tablet, a smart contract is instantly activated in the blockchain network. This automatically initiates payment for the transport company's services. This eliminates entire departments of paper bureaucracy, makes document forgery impossible, and reduces the waiting time for carrier payment from several weeks to mere minutes. To summarize our lecture today, I want to emphasize the main idea. A modern transport management system is much more than just an electronic map or a convenient schedule of trips. It is a powerful analytical tool and a true ecosystem of efficiency that works as a single seamless mechanism. You can imagine this ecosystem as a kind of shield that reliably protects business profits and service levels. It consists of 4 critically important elements that cannot exist without each other: a tariff management module, mathematical routing, operational telematics, and deep end-to-end analytics. When we combine these components, we take a fundamental management step. We definitively replace vulnerable human intuition with flawless mathematical algorithms. Thanks to this synergy, the company gains absolute transparency for every kilometer of the journey. We know exactly where the cargo is, how much fuel has been consumed, and whether temperature regimes or other transportation conditions are being violated. However, the ultimate goal of implementing all these complex IT technologies, neural networks, and telematics sensors is not just about the banal reduction of costs. The main thing is impeccable service and the highest reliability for our client. When we keep our promise and deliver the goods precisely within the agreed time window, we build long-term trust. Thus, the use of TMS allows us to transform logistics from a difficult, manual, and error-prone process into a powerful digital advantage for the enterprise in today's extremely competitive market. This concludes our review of transport management systems. Thank you all for your attention. I hope this material helps you better understand the hidden mechanisms of modern supply chains. See you at the next class.